డాక్టర్ బిఆర్ అంబేద్కర్ సార్వత్రిక విశ్వవిద్యాలయం విద్యార్థులకు స్వాగతం. ఈ ప్రసారంలో
Hello students, we are going to have a video lesson on specific heats of solids. The definition of a specific heats of solids is the quantity of heat that is required to raise a temperature from through 1 degree Kelvin is called specific heat. Specific heat is evaluated for gases, liquids and solids. Here the problem is for solids alone. You will be observing on the monitor a particular chart showing measuring the specific heat capacity. In this you will have the instrument diagram that is being shown here. This is called differential scanning calorimeter. The calorimeter scan output is shown in this particular one. Like this, they will take the measurements of specific heats. After measuring the specific heats for different temperatures, we will be able to analyze them. The specific heat is generally called as CV, that is specific heat at constant volume. In the case of solids, CV and CP happens to be very nearly same. So CV is equal to dou Q by dou T at constant volume. Q is the quantity of heat and the associated energy is given in the form of E by dou T at constant volume. So here for solids, Cp is nearly equal to Cv and the corresponding specific heat of solid is divided into two parts. One is when the electron takes the heat energy, it will have the specific heat for electron and the lattice takes the energy, so it will be lattice specific heat. So for a solid, the lattice specific heat and electronic specific heat, these two are there. Now the Cv is equal to internal energy of the material, also called as U, du by dt, that is equal to 1.5 R, which happens to be in the values of joules, 12.5 into 10 to the power of 3 joules per kilomole degree Kelvin. Here classical theories of heat or thermodynamics give the values of specific heats in the form of the amount of heat associated with the matter. So Dulong and Petit are the two scientists who worked on the classical theories and also on thermodynamics. There are classical statistical methods, quantum statistical methods and thermodynamical methods. So in all these things, the Cv value is equal to dou E by dou T at constant volume is equal to 3R, where R is the gas constant. Dulong and Petit will give the numerical value as 3R. Heat capacity in the classical thermodynamics is given as, it does not tell us anything about the heat capacity of solids at finite temperature, but we know that it must vanish at 0 degrees Kelvin. At 0 temperature, all the atoms do not take any amount of energy, hence there will not be any absorption of heat. Consequently, the specific heat also should not be available. Now in the monitor we will be observing a particular diagram showing that the atoms, this is particularly a diatomic solid like probably alkali halide, NaCl. So here this bigger ion is Na and smaller ion is Cl. There are spring like things provided in this model, but actually there will not be any springs between the atoms, but there will be a electromagnetic force between one atom and another atom in a given molecule. atoms have got protons and electrons. Hence, the electromagnetic force will make the amount of energy associated with them, between them, is the electrical energy, and that energy will make the atoms to vibrate. When they are vibrating, they will have their what is called kinetic energy, shown in the monitor as half mv square, and as a potential energy shown in the monitor as half gamma x square. So the average energy is taken as 3 Na kBT. Here kB is the Boltzmann constant, T is the temperature, Na is the Avogadro number. Cv is equal to dou E by dou T, that happens to be 3R. Now what is happening? These atoms will be vibrating. When they are vibrating, they will have the vibrational energy, and hence Dulong and Petit, they have introduced the idea of atomic oscillators. When they vibrate with the same frequency of different amplitudes. The internal energy U contributes to the vibrational energy. This is the photo of Pere-Louis Dulong. And Dulong and Petit's law happens to be useful mainly at room temperature and little higher temperatures. In those days, the low temperature experimental data was not available. Consequently, they have provided this law, and this law states only 3R value for all the materials. But you see in the monitor a diagram, a graph showing for lead, aluminum, carbon in the form of diamond, and silicon, all these things for their temperatures varying from very low to higher values. As they are going to higher values at room temperature and above, they all become constant as suggested by Dulong and Petit law. But when it is at the lower temperatures, they are deviating from Dulong and Petit law. This happens to be the big lacuna in trying to understand specific heats of solids at lower temperatures for the scientists. Now, in the monitor you will be observing heat capacity of a diamond. This is Dulong and Petit value is a fixed constant value as shown here, and at lower temperatures these dots are being provided as experimental value, and this has to be satisfied with the associated theory. There is no theory available to this until 1907 when Einstein has introduced it. So Einstein model of a solid is based on the concept of quantization. The word quantum was introduced by Max Planck in 1900 to explain the energy associated with a cavity resonator. Here the cavity resonator, the energy is limited only to cavity resonator, whereas Einstein in 1905 explained the photoelectric effect using the concept of quantization of Planck's idea to the photoelectric effect, and successfully explained, satisfied with all the experimental results. Hence, that was the first success of Planck's quantum concept. Now later on, the same concept he has tried to take, but this time instead of using the energy in the form of radiation, he tried to use in the form of a solid experiencing the heat energy, producing the vibrations, the associated vibrational energy is being taken in the form of quantum. Here the Einstein's concept is that he proposed the energy values of atoms and which are quantized, and proposed the simple model. The model is each atom is independent and each vibrates in 3 dimensions. Each vibration has energy, and the associated energy En is equal to n epsilon, and where n equal to 0, 1, 2, 3. Here 0 means there is no available energy at all. Epsilon is equal to hf. H is a Planck's constant, f is the vibrational frequency. Einstein, who introduced the concept of quantization into the solid matter for the first time, hence he has taken the vibrations to be essentially longitudinal vibrations. Now, the concept of longitudinal vibration is shown with the help of a model. This is a spring with a little weight. You are observing that this is oscillating. So, the direction of oscillation and the direction of propagation are the same to get the longitudinal vibration. Now, I will try to show you the concept of what is called transverse vibrations. Look to the model now. The rotation of this bar introduces what is called a shearing force on the spring. If you pull it down, even then there is a shearing force. That means the direction of the force is perpendicular to the direction of the vibration. Hence, we will find direction of vibration and direction of propagation are perpendicular to each other. Hence, we will say that this is a transverse mode of vibration. Concept of longitudinal vibrations are understood with the help of a spring that is vibrating. The concept of transverse vibrations are understood with the help of the bar that is introduced. Consequently, we will observe that the differentiation between longitudinal and transverse vibrations. But Einstein has used a simple model using only longitudinal vibrations, and his theory explains the vibrations of all the atoms within the solid as longitudinal vibration. That means if an amount of heat energy given to the solid, they will all vibrate in the direction of the energy given to it. Now, the average energy E in the monitor that you observe is equal to sigma summation of all the individual ones from n equal to 0 to infinity En Fb of En. This is frequency of vibrations. Fb is a fixed one, which is equal to A sigma n equal to 0 to infinity En e to the power of minus En by kT. kT is the classical amount of energy. Now, Cv is written in the form of dou E by dou T, that is the change of energy with temperature at constant volume, is equal to 3R into h bar. H bar is h by 2 pi, h is Planck's constant, omega E, the Einstein associated frequency, divided by kb T. Kb is the Boltzmann constant, T is the temperature, whole square, multiplied by the e to the power of h bar omega E divided by kb T in the brackets denominator, e to the power of h bar omega E divided by kt minus 1 whole square. So, this gives us the idea of quantization of the energy, which was earlier Planck has also used in his theory of radiation. In this chart, we are seeing Cv is equal to 3R into Te by T whole square, where Te is called Einstein temperature. It is epsilon divided by K. So, this Einstein temperature is a temperature at which there is a deviation from the experimental value. You are seeing in the monitor Einstein diagram and his model. His model is a great success to a very large amount of temperature range, including the Dulong and Petit range called higher temperature range. And here you see experimental and Einstein model. The dotted line is the experimental one, continuous line is Einstein model. It is merging with these things in a greater range of temperatures. We will be observing at very low temperatures the Einstein model doesn't work. Here the specific heats of solids is empirically called T cube law. Hence, you will find experimental is this one and Einstein model is this one. So, to make that satisfied, we will find Einstein model in a given solid and a curve. This solid curve is Einstein model, and these circles are experimental values. They are satisfied up to some low temperature, whereas at very low temperature they are not satisfied. Hence, in 1912, Debye a scientist, has given another theory. In this theory, he assumed that you can see the Peter Debye's photo in this. The assumptions are the solid as a system of coupled oscillator. Instead of a single one, you will be observing them as coupled to each other, described in terms of normal modes. These are called normal modes of vibrations, taking from very low values to very high values. These modes are 3 times n. 3 times means x direction, y direction, z direction. N is number of atoms given by Avogadro number. You can see in this particular visual that these are the atoms. They are having spring-like structures here. As the heat is given in this direction, Einstein assumed only the heat transmitted in the linear direction, but actually they will experience the transmission of heat not only in the linear direction but perpendicular to that transverse direction in this way, transverse direction in another way. That means in all the 3 directions they experience. So there will be 2 transverse modes and 1 longitudinal mode. Debye has taken both these things into consideration and he developed the theory. So here omega d is the Debye frequency associated with that, and the values of the CV are shown in this. The Debye model for heat capacity is depending on this equation. E is equal to 3V k to the power of 4 t to the power of 4 divided by 2 pi square nu cube and h bar cube. This integral is from 0 to xd, where the variation is from very low frequency to very high frequency. X cube by e to the power of x minus 1 into dx. This is solved to be given to a constant value of pi to the power of 4 by 15. Hence, this equation turns out to be Cv, which is equal to dou E by dou T at constant volume for 1 mole. Cv is equal to 12 R into pi to the power of 4 divided by 5 T divided by theta d, where theta d is called Debye temperature. This is whole cube. This Debye temperature is the one which is a useful one in explaining various aspects. One aspect is the Debye temperature associated energy and the associated frequency and the associated the wavelength will give us an idea of interatomic distance. This is verified by other X-ray methods to tell the interatomic distance. Here the diagram shows Debye's model, Einstein model. Debye introduced the concept of transverse as well as longitudinal vibrations, whereas Einstein used only the longitudinal vibrations. At higher temperatures, Debye, Einstein and Dulong Petit, all the 3 they merge here. Whereas as the temperature goes down, Dulong and Petit deviates much and Einstein model deviates little. But as you go to lower temperatures, the difference between Debye and Einstein models are more and more. Hence, it is found that Debye model is more useful and effective compared to any other model. We can see here in this diagram the Cv by 3R, that is the normalized function that is shown on y-axis. T divided by Td, Debye temperature, is normalized again on the x-axis. For materials like aluminum, copper, silver and lead, for all these temperatures it has been found the Debye model is fitting into all these materials at lower temperatures also. That's how it became a success. We can also see the energy levels associated with the Einstein model, energy levels associated with the Debye model. The Einstein model uses only one single frequency, correspondingly one single energy, whereas in Debye model he uses all the 3 directions for various modes having the representation of very low energy values of the vibrations also. At low temperatures, these vibrations really matter most. And this is an experimental model curve for a particular material, and Debye has shown this particular one. So that means even in the case of Debye model, it doesn't fit exactly in all the temperature ranges for all materials. Hence, from broadly elemental materials will follow, but other types of mixed metals like alloys and other things, the deviations are to be corrected in the form of coefficients for different materials, different theories. So, in the summary, we will see Dulong and Petit law is expected from the equipartition of energy theorem of classical physics. However, it fails at temperatures low compared with Einstein temperature. If the energy in solids is assumed to be quantized, however, models can be developed that agree with the observed behavior of the heat capacity with temperature. Einstein was the first to suggest such a quantum mechanical model, whereas Debye's model is a better successful model in showing all the types of vibrations. And hence, here the introduction of quantization into the solid made us to get a quasi-particle called a phonon. A phonon is a particle like a photon. Photon is that in the radiation, phonon is that in the solid material particle vibrating with certain frequency. Hence, these specific heats of solids, this subject is very useful for further development of the quantum mechanics applied to solids. The problem of specific heats of solids started sometime in 1850, and as the measurements ability are improving more and more, having higher temperature measurements as well as lower temperature measurements, the deviations are becoming greater and greater. Higher temperatures, there was no difficulty as far as Dulong and Petit law is concerned. It is fitting into all the materials at higher temperatures. As the ability to introduce lower temperatures and consequently the lower temperature measurements of all kinds in physics, the experimental data available is not fitting into Dulong and Petit law. Consequently, the theories that need to be modified are modified by Einstein introducing the quantization concept, and later on it is improved over Einstein model by Debye in the form of taking the entire all types of normal modes of vibrations in the solid in the form of longitudinal as well as transverse modes, consequently giving it as an atomic oscillator. We call it as a phonon. A phonon is a quasi-solid particle which is following the quantization concept and introducing the idea of the vibration of the atoms in the solid.
మా కార్యక్రమాలపై మీ సూచనలు సలహాలు ఆహ్వానిస్తున్నాం. మీ సూచనలు సలహాలు మాకు తెలియజేయవలసిన చిరునామా: డైరెక్టర్, ఆడియో విజువల్ ప్రొడక్షన్ అండ్ రీసెర్చ్ సెంటర్, డాక్టర్ బిఆర్ అంబేద్కర్ ఓపెన్ యూనివర్సిటీ, ప్రొఫెసర్ జి రామరెడ్డి మార్గ్, రోడ్ నంబర్ 46, జూబ్లీ హిల్స్, హైదరాబాద్ 500033.